Good morning, this is your Stat Sensei, Mr. Spensei, and this is a warm-up on the paired t-test. First off, I want to just talk about paired data real quickly. Paired data occurs when there's a natural pairing. Usually something will be tested twice. We did this at the beginning of the year in design of experiments where we did the mosquitoes spray where one arm got the new spray and the other got the old spray to see how many bites there were. So typically speaking, something is tested twice, or there's a natural pairing, as in between a husband and their wife, or between twins, something that has a natural pairing. And that way we control for outside variables that might be influencing our study. So here we have one. To compare the mean number of lesions caused by two viruses on a tobacco leaves, the strains were randomly assigned and placed on half of a tobacco leaf, with 8 leaves receiving both strains. That keyword both, because 8 leaves receiving both, tells me that this is paired. The lesions appeared and were counted, and the differences recorded. Enter the data in the table L1, L2, and L3 of the calculator. So basically, we entered this data into L1, that's strain one, and then L2 is here, and then L3 is just a subtraction. 21 minus 18 is 3, 20 minus 17 is 3. And so I've already entered that data into my calculator. So there it is, so that y'all can see it. Let me adjust the screen just a little bit. Wrong way. Hopefully that's a little better. All right. So I have the data entered in the calculator, and I can run the test. And I'm going to run the test not on L1, not on L2, but on L3. However, even though that's a subtraction and that's what we want in the calculator, I want to show you something that you need to know. If I went up and just cleared that data out and went up to the top of L3, I could have gone blue 1 minus blue 2. So now I have L1 minus L2. So blue 1 minus blue 2. And I press enter and it populates it. So I really didn't have to enter that data, but I wanted you to understand that 21 minus 18 gave me 3. That's where that information came from. All right. So test the difference at alpha equals 0.05 to determine the virus strain one produces more lesions than virus strain two. Now, the interesting thing about this is our formula is almost exactly the same as what we were working with before. Prior, when we were working with a t distribution, we had t equals x bar minus mu s divided by the square root of n. Well, here we have the same thing, except we drop some d's on it because it's the average of the differences, the population difference, the standard deviation of the differences, and then, of course, our sample size. And in this case, our sample size is not 16, it's 8 because we have 8 pairs. So n is the number of pairs. All right. So I've gone ahead and entered that data in the calculator, and I'm going to go stat calc one var stat, and it's blue button 3. So blue button 3, because my data, I want the differences, which is an L3, and I calculate, and I find my sample mean is 2.75. My sample standard deviation is 2.3145, and of course, I have 8 data pairs. What's going to be interesting or difficult for us to maybe wrap our head around is the mu d is equal to 0. In other words, we're assuming that there is no difference, that strain 1 and strain 2 have the same. And by the way, for our level of statistics, for statistics 1, this will always be 0 when we're working with paired data. Please remember, I said when we're working with paired data, that will always be 0. Well, what type of test are we going to run? Well, we're going to run a one sample paired t-test. And once again, it's for means, and really it's for the mean of the differences, but one sample paired t-test. And if all you write is one sample paired t-test, we're going to be good with that. All right, that lets us know that you know what we're doing. Okay, so when we go to draw this thing, we know we're going to be centered on our mean because it's a hypothesis test, and all hypothesis tests are centered on our mean. Well, our mean is assumed to be 0, so we're going to be centered on 0. And in this case, we ended up with an X bar of 2.75. All right. And they said they want to see that strain 1 produces more lesions than strain 2. So basically, what we're saying is we have strain 1 and we have strain 2, and this one's supposed to have more. So strain 1 should be greater than strain 2. And that key word I used was the word more, which is right over here. All right. So when we go to plug in, we have our sample mean of 2.75 minus 0 divided by the standard deviation divided by the square root of 8. This just looks like anytime we ran a typical t-test. All right, so there's no difference here. And when we're doing our alternative and null hypothesis, it's still going to be made based on the mean, but in this case, it's the mean of the differences. So mu d equals 0, and mu d is greater than 0. And basically what they were saying here is strain 1, um, they picked some random number. They picked 100, and they said 100 is greater than 90 because they were expecting strain 1 to be greater than strain 2. All right. Once again, this will always be for a paired test. This will always be 0, and we know that for all hypothesis tests, this is equal to 0. And then this will match, except we have to have the correct inequality, which we said was greater than. Okay. All right. Um, so at this point, we're ready to run the test. So here we go. It's going to run just like we ran a regular t-test. We're going to go stat test directly to t-test. We have data in there, and our mean we set at 0 because that's what we claimed right here. Our data list is an L3, so blue 3, because that's where our differences were. So wherever you have your differences, wherever you have the 3, 3, 4, 6, -1, etc., that's where we want it. We need the greater than highlighted, and we press calculate. Well, it turns out I get a t-statistic of 3.360 with a p-value of 0.006. So because it's just a one-sided, it's the probability that t is greater than 3.3605 equals 0.006. Well, our alpha value was given as 0.05, and so we see that our p-value 0.0060 is less than our alpha. So our decision is to reject the null. All right. So that's our decision. That's warm up. I hope that helps give you a good understanding of what's happening when we're running the pair test. Also, this can be done in your notes spiral. Thank you. Look forward to seeing you on the next one. So continuing on to the next one. The next one is we're going to run a confidence interval for the same thing. It says create a confidence interval for the difference in the number of lesions, strain 1 minus strain 2. We always have to put the order that we subtracted in, all right? So we went strain 1 minus strain 2. Well, our formula is much like we used before, all right? Prior to this, our our confidence interval had this formula for a regular t-test, x bar plus or minus t star s divided by square root of n. So that was what we had before. So the only real difference is we drop some d's on it. We put a d for the sample mean, a d for SD, and of course that's our number of pairs. T star is going to work the same way. So let's go ahead and calculate T star. We're going to have to go second vars, inverse T, and in this case, we're doing a 99%. So parenthesis 1 minus 0.99, close parenthesis, divided by 2. And degrees of freedom, we need to be careful with this. Degrees of freedom is based on our pairs. So we have 8 pairs. We don't want to say that we have 16 values. We have 8 pairs, all right, because that's what we entered into the calculator. So we have 8 minus 1, and that gives us our degrees of freedom. So in this case, we ended up with 3.4994. Please always make that value positive, okay? Just the way we work it ends up being a negative value, but we don't want it that way for running this. All right, please remember all so there's our list of information. We already had that from up above. Now that we have that, we can go ahead and plug that in. And so when we plug in 2.75 for our X bar, it goes here. Right here, we have our T star and our standard deviation of the sample, 2.3145, and the square root of 8. And just in case you didn't remember where we got that, I went stat calc 1 var stat and stat calc 1 var stat. Make sure that that's on L3, so blue 3 if it's not. And the reason it's blue 3 is because that's where our differences are. And so that's where that information is. And here's what I meant by our differences. All of our differences are L3. We don't want the individual values. We want the differences. Okay, when we go to draw this thing, please remember all confidence intervals are centered on X bar. So if this is X bar right here, I need to be centered on that. So my X bar right here is 2.75. We know we're going to have a lower bound and an upper bound, and we're looking for 99% being in here. So what type of test are we doing? Well, we're working with a one sample paired T interval. And it's a one sample paired T interval for the mean of the differences. But right there, if we have one sample paired T interval, we're going to be really happy about that. Let's go ahead and run this thing. Stat test, and we're going to run this just like a regular T interval. We're going to go to number 8, press enter. We have data. Our data list is an L3, so blue 3 if yours says something else. And we wanted a 99%, so 0.99. When we do that, we get negative 0.1137 and 5.6137. So that's our lower bound and our upper bound. And I want to say something about that. Because 0 is contained, we cannot say that there is a difference, all right? We cannot say there's a difference. Now, I will say this is we have more positive than we have negative, so it looks like strain 1 has more than strain 2, but because 0 is contained, we're not 99% confident. So we can't say that there is a difference between them. All right, appreciate you watching. I'm sure hope this helped. Thank you.